Although we've introduced the harmonic oscillator as a model for diatomic vibration, it's useful to look at this and compare it to what we might normally expect. So what we have is basically a model for two masses that are held together by some kind of restoring force, which I've drawn here as a spring for a harmonic oscillator. I'll remind you this is M1 and this is M2, and we could write the energy of this as equal to 1/2 mu v squared plus 1/2 mu omega squared r squared, where r is the displacement between them. I could also write this as 1/2 mu p squared plus 1/2 mu omega squared r squared, and this is maybe a little bit more directly related to what we would see in quantum mechanics. Okay, so how does this really relate to what we might normally expect to see in a diatomic molecule? Well, one of the things that we know from earlier studies, I would guess, is that if we apply enough energy to this pair of masses, we could actually break them apart. So there is the possibility of dissociation at higher energies. And that's something that a harmonic oscillator cannot do. So I've drawn a picture over here on the right. Actually, I didn't draw it. I pasted it in, but I want you to focus on the blue curve to begin with as a picture of what a realistic potential between two masses might look like. And in particular, there are some features that are very specific ones that we would expect to see in a case like this. For example, as the potential changes, I'm going to denote this point up here as representing energy equals 0. So in other words, this is a negative energy down here, negative energy. And V of r will go to 0 as r goes to infinity. So as we get to larger and larger r, we expect to see this potential get up closer and closer to 0. Similarly, as we go to small r, so as r goes to 0, as we push those two masses together, we ordinarily expect the potential to get very large, and indeed that's what we see here in this blue curve. So we're going up to very high potentials as r goes down to 0. And finally, we have a point where there's a minimum. And that minimum point is something that occurs, we'll say, at a position r equals to r sub e, okay, which is drawn here. And that point is known as the equilibrium point for the potential. Another thing that we normally see at that point is that the derivative of the potential evaluated at that point is going to be equal to 0. In other words, it's a flat slope at that point. So we expect to see that. So now, how would we relate this to the harmonic oscillator? Why would we think that a harmonic oscillator would be anything like that? All right, well, what we're going to do is we're going to write our potential function as a power series expanded around this point. So in other words, that means the first term will be just equal to the potential at that point. The second term will be its, I should leave that as a plain derivative, will just be its first derivative evaluated at that point times r minus re. The third term would be the second derivative of the potential at that point times r minus re squared, and so forth. And if I want to do the next higher term, it'd be 1/6 of the third derivative of the potential. And there are higher order terms, of course. All right, so how can we relate these different terms? Well, we know, first of all, that this term is just going to be 0 because we've already said that the slope at that minimum is 0, so we can get rid of that term altogether. This term is just a constant, and in fact this constant is, in some sense, since it's down here it's related to the amount of energy that is required to add to the bond to dissociate it. So this is like a dissociation energy, but really all it does functionally to the potential function is to shift it up and down. So this is just a vertical shift in that potential function. All right, what about these next terms? Well, this term, I hope you recognize, this is going to be a constant when we evaluate it at this value RB. So that's just our constant K, which we've already remarked is equal to mu omega squared. This is just our displacement squared. So this was something that we labeled as R squared in earlier video. So what we have here is that this second term is the harmonic oscillator. And the higher order terms here are going to be terms that go beyond the harmonic oscillator, and so they add in what we would call anharmonicity to our potential function. Anharmonicity being something not harmonic. All right, so what this tells us, and now I'll point out the green curve here, is the harmonic oscillator that fits the bottom of this realistic potential energy curve. All right, so we can see that the harmonic oscillator is a great fit, is a great model for the potential down here at low energies. So low energies, we basically have a harmonic oscillator. But as we go to higher energies, we begin to see divergence between the blue curve and the green curve. So we're seeing a growing gap between these two curves as we go to higher and higher energy. And that happens on both sides. It's happening up here on the high R side, but it's also happening on the low R side. And you'll notice that, in fact, we go from having the harmonic oscillator being the higher energy curve over here on the high side to it being the lower energy curve. In other words, directly below the position of the realistic potential surface. So what this is all telling us is that the harmonic oscillator is going to be a great model down at low energies, but as we go higher in energy, we should expect that it will not be as good a model for what's going on vibrationally, for any sort of coordinate. Now, this basically summarizes when we can use the harmonic oscillator model as a realistic model for vibration and when it might be less good to do it. Now I want to point out a few other things that are some correspondences here between different ways of expressing this harmonic oscillator model. We've noted that K is equal to mu omega squared, but we also know that the angular frequency omega can be written as 2 pi times just the regular frequency. So in other words, K could also be written as mu omega squared or as 4 pi squared mu nu squared. So this is an equivalent way of expressing the force constant K. We also have seen that this force constant K is the second derivative of a realistic potential with respect to the displacement coordinate, but evaluated at that equilibrium value. So I hope this gives you some feel for where the harmonic oscillator model fits in when we start talking about real vibrations. We'll be talking about this a lot more in a later module, Module 5, and then again in Module 6 when we talk about molecules. But I wanted to set this straight now so that we understand that the harmonic oscillator is a beautiful, simple model. It's good for describing qualitatively certain things about molecules, but there are limits to its usefulness.